Today is week 12 of our discussion for GATE preparation, previous year questions, and today we'll discuss fluid mechanics. So we'll discuss three questions today, all previous year questions, and they will be on open channel flow. So we'll look into some concepts that deal with the uniform flow and when there is a hump or there is a channel constriction, and maybe we'll look at some derivations along the way. So let's start. GATE 2008, question number 71. A rectangular channel 6 meter wide carries a discharge of 16 meter cube per second under uniform flow conditions with normal depth of 1.6 meter and Manning's constant, that is the N, is given as 0.015. So the first part of the question is, so the 71st question is the longitudinal slope of the channel. So this is a pretty simple question. If we know how to substitute the form in the formula for Manning's equation to calculate the flow, we can easily solve this question, and that's what we are going to do. So the Manning's equation for velocity is given as v equal to 1 by n r to the power 2 by 3 s to the power 1 by 2, or in this case s naught because we have uniform flow, right? What is r? R is nothing but hydraulic radius or hydraulic depth, and it is given by A by P, where A is the flow area, P is the wetting parameter, wetting perimeter, right? So in this question, we are given a rectangular channel, right? So let's draw that. So this is the width B, and this is the flow depth Y. So the area of flow will be B into Y, and the wetting parameter will be B plus 2Y. So this is the wetting parameter, and it is given as B plus 2Y. So let's solve this question. Same way as we wrote the velocity formula, we can write the formula for the discharge as Q is equal to A into V. So Q is equal to 1 by N A R power 2 by 3 S naught power 1 by 2. Right, so let's put the values in this formula. Q is nothing but 16 meter cube per second is equal to 1 by N, that is 0.015. A is 3, no sorry, the 6, that is the width, into the depth, that is given as 1.6, and R is nothing but A by P. So it's 6 into 1.6 divided by 6 plus 2 into 1.6 to the power 2 by 3, and S is the slope that we have to calculate. So when we solve this formula, we will get the value of S naught. Right, so let's simplify this and let's try to solve. So I'm going to use the standard calculator that we use in GATE. So I'm using it in my Android mobile. I always say, also in my first class, I had told you guys that if you are doing these calculations, you are doing these numericals in your practice, better to use GATE calculators so that you are familiar with it by the time the exam comes, right? So yeah, let's solve. So let's first simplify the value for r to the power 2 by 3. 6 into 1.6, that is 9.6 divided by 6 plus 3.2. So r is 1.0434. And then we have power 2 by 3, that is 0.667. That is 1.028. So we have here 9.6 divided by 0.015 into Yeah, so we have here 9.6 divided by 0.015 into 1.028 into S naught power 1 by 2. That is equal to 16. And when you further simplify this, the expression that you are going to get is, let's just do the final calculation and write the value of our bed slope for this uniform flow. Right, so this will go here in division and into 16 divided by 9.6 into 0.015. Then we have to do the square of that. So the final answer will come 0.000590. So this is the bed slope, and that is the answer to our question, S naught. So the closest to this value is our option A, that is 0.00585. So that's the answer. Okay, so Shailene, you have joined. Uh, so let me just describe what we are going to discuss today, what we are discussing today. So we are going to discuss open channel flow. We are going to see three questions and only three questions today. And these questions will be related to open channel flow. First is a simple question. We just calculated the value of the bed slope using our Manning's formula. And the second and third question, we are going to see what happens if we have a hump and what happens if we perform channel contraction in a open channel flow. And then maybe later we'll see some derivations. Okay, so this was the first question. We calculated our slope. Let's move on to the next question. So these are all are no this is a three-part question actually in GATE 2008. So 71, 72, and 73 we are discussing here. But the first part is not related to the second or the third, right? So it is an independent question actually, but they just gave it as a three-part question. Okay, so let's look at the second question. So I have copy pasted the detail for each of the part. So the we have a rectangular channel which is 6 meter wide and that carries a flow of 16 meter cube per second, and the depth is 1.6 meters, and the Manning's coefficient is 0.015. Okay, now the question is, a hump is to be provided at the channel bed. The maximum height of the hump without affecting the upstream flow condition is. Okay, so if you remember that, let's look at our height and specific energy diagram. So this is 45-degree line or 1-to-1 line. This is our diagram for Y and effective energy. Sorry, specific energy. I mean to draw it like this. Yeah. So we have, let's say we have at some stage, this is the stage, and we have energy E1, right? So this is the line. We have energy E1. And when we install a hump, this is our channel, this is water flow. When we install a hump, since this is a uniform flow, the total energy line is going to remain same, right? The total energy line with respect to our bed slope is going to remain same. So when we install this particular hump, what happens is this was, oh sorry, this was our E1 before the hump, and this is our E2 after the hump. And the difference between this E1 and E2 is going to be delta Z. So the relation that we have to remember when we are performing this channel, giving a hump in the channel, is that E1 is equal to E2 plus delta Z. So this is our E1 in, let's look at our Y versus E graph. So this is our E1 at some stage. Then when we give a hump, we reduce the energy, the specific energy by delta Z. So this is our E2. and this is delta Z. So if you have a subcritical flow, or let's look at subcritical and then supercritical later on. If you have a subcritical flow, the depth of flow, that is y on the y-axis, is going to reduce, right? So your energy, your specific energy has reduced from E1 to E2, and corresponding to that, your depth of flow is going to reduce. So that means if you look at your flow depth in these two cases, this is the one before your hump, and the one after your hump is going to be slightly lower than this if you have a subcritical flow. So y1 is greater than y2. Okay. Now, if you have supercritical flow, then still you are reducing your energy from E1 to E2 by delta Z. But looking at this graph, we can see that the flow depth is going to increase. So y1 is going to be less than y2. So it all depends upon whether your flow is subcritical or supercritical. So let's look at this subcritical flow and see what happens if we provide excessive hump. So we know that when we provide hump, the depth of flow is going to reduce on the downstream side, right? On this side, the depth of flow is going to reduce. But if we keep on providing the hump and keep on reducing the specific energy, if you see here, there will come a point when these uh, when we come at the most extreme point of this plot, that is this critical point. What happens after this is when you provide any more hump, the downstream depth is not going to change. It is going to remain y2 is equal to yc, right? And the upstream depth y1 star is going to increase so that the difference between your E1 minus E2 remains delta Z. So what happens? You keep on giving your hump, you keep on increasing your delta Z. Your depth on the downstream is going to keep on decreasing. But as soon as you give the maximum allowed that we are asked in this question, as soon as you give this, the y2, the depth on the downstream, will become the critical depth, and after that, even if you increase your delta Z, your downstream depth is not going to increase. And when that doesn't increase, your energy on the downstream, that specific energy on the downstream, is not going to increase. It is also going to be remaining at the specific energy at critical state. But we know from the concept that E1 minus E2 has to be delta Z. So to compensate for that, E1 is now going to increase, and correspondingly Y1 will increase. So in this question, we are not asked what happens if we go beyond that delta Z, but what we are going to do today, we are going to calculate that delta Z max, and then we'll finish this question. Then we are going to introduce a delta Z that is greater than this delta Z, and then we'll see what happens to the and how do we calculate the depth at the upstream. Okay, so let's start this question. So let me erase this. Okay, so according to this question, we have to calculate our delta Z max at the downstream. What is the property that we know? At delta Z max, Y2 will become YC. That means E2 will become EC. Okay. Okay. So there is a standard formula to calculate the critical depth in rectangular channel, and that is Yc is equal to Q square divided by G power 1 by 3. Then what is this Q? This Q is the discharge per unit width of the channel. So this Q for us, the big Q that is given to us in this question, that is 16, and the width of the channel is 6 meter, that is also given to us. So we have 16 by 6. And G is the standard acceleration due to gravity, that is 9.81. So when you solve this, you get the formula for your critical depth as 16 divided by 6, 2.67 square divided by 9.81 cube root, 0.898 meters. And correspondingly, so the standard formula for E2, or not for E2, the specific energy is Y plus V square by 2G. But for in the case of critical depth and in rectangular channel, we have E2 as a simple formula that you can remember, 3 by 2 Yc. So that is, from this formula, we can easily get the value of E2, that is equal to EC, that is 1.347 meters. Okay, so this is your uh, depth at, or depth and the specific energy at the downstream side. So if I want to write here, let me write your Y2 is 0.98, sorry, 898, and your E2 is 1.347. Okay, your Y1 is given to you 1.6 meters. So can we calculate our E1? Yes, we can calculate our E1 from the standard formula for specific energy, that is Y plus V square by 2G. 1.6 plus, what is V? V is nothing but Q by A, right? So since we are given the Q, let us write it in that format. So V square is Q square by A square. So 6 into 1.6 square into 19.62, that is nothing but 2 into G. This is your E1. Okay, so let's solve this. We have 1.6 plus 16 square divided by 6 into 1.6. So let's solve this plus 1. Yeah, so we have 1.741 meters E1, and E2 is this. Okay, so this is our, let me draw again the line. This is our bed slope. This is our hump. This is the total energy line above the bed slope. E1 is 1.741. E2 is 1.347. Then can we get the value of delta Z? Delta Z, that is in this case delta Z max, is going to be E1 minus E2, or in this case EC, is 1.741 minus 1.347. 0.394 meters. So this is approximately 0.4 meters, and that is the option that is given to us, which is correct answer. Okay, so what did we learn from here? We understood that whenever they are asking us to calculate the delta Z max, we just have to calculate our critical depth, get the energy corresponding to the critical depth, and then calculate the energy for the given depth at the upstream side, and the difference of these two energy is going to be our delta Z. Now, now we know that for point 0.4 of delta Z, we will get a critical depth at the downstream side and the upstream will not be affected, right? So let's now see that if we give a higher depth, say 0.5 meter or the higher height of the hump, what happens to the upstream? We know the upstream is going to increase. Let's now see how much it is going to increase. Okay, so let me erase this. You can easily see this from the recording. So since I am in home, actually in my hometown right now, we had the session on last Sunday. I didn't, none of you guys joined. So the session is still with me. I am unable to record because the internet is not that strong here. So uploading 1 GB file in YouTube is it's always gets stuck at some point. So I will upload the recording as soon as I reach campus. Okay, so now let's look at this new question. So we have delta Z as 0.5 meters right now. Okay, and the other things are same. Q is 16 meter cube per second. B is 6 meters. Y1 is 1.6 meters. That is given in the question, so I am writing just for information, but we know that Y1 is going to change. And N is 0.015 meters. Okay, so we have been given these things. Now, when Z is 0.5 meters, then we know that the depth on the downstream is going to be YC. Hmm? From our earlier question, we have seen the value of IC as 0.898, I guess it was. Yeah, luckily I wrote here 0.898 meters, and correspondingly EC was 1.347 meters, right? So that means even after increasing the hump more, if this is the same, if the depth on the downstream and the specific energy is the same, so the E1 is now needs to be recalculated. So E1 will be EC plus delta Z. So we have 1.347 plus 0.5, that is 1.847 meters. Now when E1 is changed, the depth in upstream has to change to accommodate for this change. So we have 1.847 is equal to y1 plus. So again we are going to write the velocity in terms of the flow, q square divided by 6 into 1.6 square, this is the area, into 19.62. So let's put the value of q also. This is 16 square. So we are oh yeah, my apologies. Here it's not going to 1.6 since the depth of flow in the upstream is going to change. So it is going to be 6 into y1 square. 6 square into y1 square and 19.62. Right? So we are going to get a cubic equation in y. So let's see what is this cubic equation that we are going to get. And this is one of the reasons why I feel that this problem is not going to be there in any of the gate exams, because you see, solving a cubic equation, there is no straightforward method that I am aware of, or I think there is. So I don't think this is going to be there, but it can come in other examinations. So we can be we can easily calculate it, so that we need the concept. For that we are discussing this question, or maybe maybe the cubic equation that we'll end up with finally for the questions that will be framed for gate is going to be very simple. So, that kind of question can also come. So the cubic equation that we are going to get for this y1 is y1 cube minus 1.847 y1 square plus 0.36, sorry, 0.3624 is equal to 0. So this is the y1 cube. Now, if you try to solve this question, or if you plot this with y, you will see that, so this is your fx, and this is, or maybe this is your f y1, and this is your y1. You will see that the plot is going to be cubic, but at 1.6 the value is negative. The value of this function at 1.6 is negative. That means y1 is greater than 1.6 only is going to suffice, be the root of this cubic equation. So I just tried by hit and trial. I tried the value 1.7 and we still got the value as negative. So this value of y1 is coming to be around 1.73 meters. That is greater than 1.6 meters. That was the original depth in the upstream. So now we know how we have to calculate the upstream depth if the channel is provided with hump which is greater than the maximum allowed hump. Okay, yeah. So we can try this. Or maybe if it comes in a gate as a multiple choice question, then we can, uh, do substitution and identify which is the correct option. That is definitely one of the possibilities in which it can come. Okay, so this is our additional part of this question. Now let's go to the channel constriction, which I feel, I don't know why, but I feel that this is a little more complicated than the hump in a channel. Let's see how we solve this. So this is the detail that is repeated information. So we have a rectangular channel. The width is 6 meter. Upstream flow depth is 1.6 meter. Flow is 16 meter cube per second. And n is 0.015. Basically, we don't even need n right now, so I'm not going to write that. Okay. Now, so let's look at the question. The channel width is to be contracted. Now, the minimum width to which the channel can be contracted without affecting the upstream flow condition is. So similar to the above question where we provided the hump and it asked us the maximum delta Z so that the upstream is not affected, and that means that the downstream is just y2 is equal to yc. This question is asking us what is the maximum contraction or the minimum width V2 so that the upstream is not affected. So this is the top view actually, so that the upstream is not affected, and that means that again y2 is yc. Okay, so let's see what we can do. Before going to that, we are going to look at one graph that is going to be between y and discharge per unit width q. This graph looks like this. So the above part is subcritical flow, the below part is supercritical flow. So when you have a channel, top view is like this. The flow capital Q is going to be constant in both of these sections, right? But the flow per unit width is going to be different. So basically, Q2 is going to be greater than Q1 because the width is less here. So the denominator is less for this expression. Q is equal to Q by B. For this expression, we have uh, a lesser denominator. That's why we are going to have Q2 more than Q1. So let's look at this uh, graph here. Let's look at this plot here. You have one Q1 here, and when you are providing some kind of constriction, you are increasing it to Q2, right? This is Q1, this is Q2. When you do that, you are actually again reducing the flow depth. So this is going to be your Y1, and which will be higher than your Y2, right? That means if you provide constriction in your channel, your upstream depth is going to be more and downstream depth is going to reduce. One more important thing to note here is since there is no hump in this particular channel constriction question, the specific energy in the upstream and downstream in case of uniform flow is going to remain the same, right? So this is one point that we have to remember. Since there is no hump, and in case of uniform flow, our total energy line remains at the same height for uh, throughout the bed slope. It is means that the specific energy is going to remain same in the upstream and downstream condition. Okay. Now using this information, okay. So one more thing before we go into the question. Now, they have asked us to calculate this B minimum. That means at this B minimum, Y2 is just going to touch the YC, that is the critical depth. But what happens if this B is less than B minimum? In that case, Y2 is going to again be YC, but this YC is not going to be the same YC as earlier. So in case of our channel hum, the YC remains same, right? The critical depth remains same when we increased, when we provided different or higher value of our delta Z. But in the case of channel width contraction, YC is going to change because look at this formula. How we calculate YC in case of our rectangular channel? We calculate it using Q square divided by G power 1 by 3. What is Q? The small q is nothing but Q by B square divided by G power 1 by 3. Now, Q, that is the flow rate, the capital Q is not going to change, right? Just because we are constricting the channel is not going to be changing the flow rate. There is no storage here. Whatever is coming into this constriction, it is going to go. That means if you reduce your B, your this expression value is going to change. So whenever you are given a different width in the downstream or a higher width from your minimum allowed width, your YC is going to be different YC. So your Y2 is still going to be your critical depth, but the value of that depth is going to change. And similarly, your E2 is going to be your critical energy, but the value is going to change compared to your B minimum. And since we know that E1 is equal to E2, so in this case also your E1 is going to be your nu E star. So what is this? This is when your B is less than your B minimum. When your B is equal to B minimum, your E1 is not affected. So E1 will be y1 plus the standard y1 plus v1 square by 2g. But in this case, since your E1 is also changing, your y1 will also change. Okay. So let's look at some questions to understand this. So first, let's solve the given question to us, and then we will understand through another question where we have the downstream channel width lower than the minimum allowed width. Okay, so so these are the standard information that is given to us. So let's draw the channel. Let's give this downstream width the value B. So the Q1 here, the small q, that is flow per unit width, is going to be 16 by 6, that is 2.67 meter cube per second. And this q is 16 by B. Now B is, in this case, B minimum. So Y2 is YC. Now let's use the formula for YC to calculate our no to get the B. So we have 16 by B square divided by 9.81 to the power 1 by 3. This is nothing but Q square by G to the power 1 by 3. Okay. Okay. So when we have rectangular channel, we know that the energy is going to be 3 by 2 YC. So it is nothing but 3 by 2 Q square, or maybe let me write it as, simplify this expression. So 16 square divided by 9.81, and then the cube root of that. So we have 2.966 divided by B to the power 2 by 3. Or let me choose the partial eraser here, otherwise it is going to erase everything. Yeah, B to the power 2 by 3. Now, what else do we know? We know that at B minimum, E1 is not affected. So can we calculate E1? Let's calculate our E1. It is nothing but Y1, that is 1.6 plus V1 square by 2G. So this is actually going to be same as the one which we calculated in the first question. So if I have somewhere here the E1, we can directly use it. Okay, so it seems that I have erased that. So no problem. Let's calculate it again. So we have 1.6 plus V1 square is 16 square divided by 6 square into 1.6 square into 19.62. So this is going to be our 1.741 meters even. What else do we know about channel constriction? We know that E1 is equal to E2 because the total energy line is going to remain same, and since there is no hump, we are not going to see any change in the total energy, specific energy. So let's equate the two and get our B. So when you solve this expression, you will get the value of B as 0.3 0 point, sorry, not 0 point, yeah, 4.085 meters. And the value closest to this is 4.1 meters. So this is your answer, right? This is how you calculate. So what we have seen for calculating B minimum, we calculate the Y critical first. First we calculate the Y critical, then we calculate the E2, we calculate, oh my God, again the internet connection. Okay, luckily it has come back. Yeah. So yeah, I hope my screen is visible. So we calculate E1 and perform E1 is equal to E2 and get the value of B minimum. Okay, good, great. Let's look at one scenario when we have B2 less than B minimum. So B2 less than 4.1 meter. To be safe, let's take B2 as 3 meters. Now let's solve this question. So this is our channel. What do we know now? The thing that we know is upstream things are going to change, right? In the upstream, we will not have y1 is equal to 1.6 meter. Y1 is unknown now. Downstream, we know y2 is going to be yc, but this yc is not same as this yc, right? This yc is going to be different. So let's calculate this new yc. We have 16 divided by 3 square divided by 9.81, 1 by 3. 16 divided by 3. Then we have square of that divided by 9.81 and 1 by 3. So this is 1.4259 meters. Correct me if I'm wrong here. I think it is correct. Yeah, I think it is correct. Let's see. So the value of E2, that is EC star, is into 1.5, that is 2.138 or 2.139 meters. Okay. Now when you know these two, to calculate, oh my God, uh, so and when we know these two, to calculate the value of your E1, you just have to put E1 is equal to E2 and we can easily calculate our value of Y1. Okay, so we have here Y1 plus Q. So again, we are going to write the velocity in terms of our discharge. So A is going to be 36 into Y1 square into 19.62 is equal to 2.139. Right, so again, it is going to be a cubic expression in y. So y1 cube minus 2.138 y1 square plus 0.3624 is equal to 0. Yeah, this is going to be a cubic expression. Again, I used some kind of approximation here, and the y1 value now is going to be approximately 2.05 meters. So the value of this expression Fy1 was negative at 2 and it was positive at 2.1. So I have just approximated the value of Y1 as 2.05 meters, right? So what does that mean? That means that upstream depth has increased from 1.6 to 2.05 meters due to excessive contraction on the downstream side. Okay, now let's look at two derivations here. First derivation is your YC in case of rectangular channel, we have written as Q square divided by G power 1 by 3. Actually, when you want to calculate your critical depth, you should use the formula Q square T divided by GA cube is equal to 1. But when you simplify this formula, in case of rectangular channel, then you can do away with this. So how do we get from there to here? Let us see. A Q is the discharge, T is nothing but the channel top width, A is the flow area, and G is the acceleration due to gravity. So let's look at this expression here. This is Y, which in case is YC, as we have seen, put this expression is equal to 1. So let's use Q square. What is T in case of rectangular channel? The top width is nothing but B. And what is area? Area is B into YC. So B cube YC cube. Now, I think now itself you can see how this expression is going to pan out. So you have Q by B whole square divided by G is equal to YC cube. This implies that YC is equal to Q by B whole square divided by G to the power 1 by 3. So don't always use this formula for critical depth. Only use this when you have a rectangular channel. Second derivation is this derivation itself which we used here to get the value of YC. Okay. So we know that our specific energy is written as E is equal to Y plus V square by 2G. Let us write it in terms of discharge. Y plus Q square by 2G A square. Now, from this diagram, the depth versus specific energy diagram, we have seen that this point, right, this point is called as critical point. And at this point, dE by dy is 0. So if you are getting confused, just rotate this plot. Let me see if I can do that here. If I can rotate it. Okay, so I don't think I can rotate it. Let me draw it again and you can try to visualize. So this is going to be like this, right? At this point, the derivative of E with respect to Y is 0, right? So let's do a derivative of this expression with respect to Y. So dE by dy is equal to dy by dy is nothing but 1 plus q square by 2g. So the discharge is going to be constant. So we are going to keep that outside with g. But the area of flow is going to change, right? So this expression is going to be 1 by, sorry, minus 2 by a cube into dA by dy, right? That means that what we have done here is nothing but d by dA of q square by 2g a square, and then we have d by dA by dy. So if you simplify this, the dA will get cancelled. But what we have done, we have not simplified it. We have actually expanded that d by dy of this expression and given introduced two of our dAs. So first we have just done the derivative with dA, and then we are with derivative with A, and then we are performing the derivative of the area with the depth. Okay, so this is our expression. Now at critical point, this dE by dy is going to be 0. So 1, if you move this 1 on this side, minus 1 is nothing but minus of q square by ga cube into dA by dy. So this particular thing is going to get cancelled. Now in a channel, right, in a channel, if you see this, this is the area, right? This is the area. If you look at small depth at the top of the channel, very small depth, that is dy, and you look at this, so this will be small area, that is dA. So dA is going to be nothing but the top width of the channel into your dy. So from here we can see that dA by dy is going to be equal to your top width. So 1 is equal to q square t by ga cube. Now I have always had this doubt, and it is still, I couldn't find any proper clarification, and I am also going to leave you with this same doubt, that why do we look at this element for this cross section in a channel at the top? Why don't we look at it here? If you do that, we cannot put dA by dy. So if we do that, this small area dA is going to be some width b into dy, right? And in that case, dA by dy is not going to be equal to t. It is going to be equal to some unknown value b, right? So if you can find out this, then better. If you don't, if you're not able to find that out, it doesn't matter. It's not that important. We just see how, we just know how this derivation is obtained. Yeah, Shailene, you wanted to say something. Yes.
Yes, sir. Here we are dealing with the rectangular section, right?
No, it is actually general. So no matter if it is a rectangular channel or anything, trapezoidal channel, whenever there is a critical flow, this expression is valid. If it is rectangle, then it is very simple. dA by dy is always going to be constant, that is going to be b, and this that is same as the top width also. But this expression, q square t by ga cube, is valid for all type of channels, triangular, rectangular, or uh, trapezoidal, for everything. Yeah, so if you can, look into it and try to find out, you can put it in the, or maybe you can tell me next time, or you can put it in the comment in the channel, you know. Okay, so that's all that we are going to discuss today. I hope it was valuable, it was informative, and you learned something today. One more thing. So today is Deepavali. So again, I wish Shailene, who has joined, thank you for that. Happy Deepavali. And 4-1-0. I think we are going to win today's match also. So let's hope we win this World Cup also. Okay. Thank you.
Yeah. Happy Diwali, sir. Thank you.
Happy Diwali.